down. Whatever goes up must come down. The illusion is that at some point, if you go high enough, this gravity they claim exists that pulls you back down to the earth, suddenly just you pop out of it and into the vacuum of space.
Well, hello and greetings from Northern Michigan. This is Bob the Science Guy. Today we're continuing our series on Eric Dubay, Zealot or Conman. This is part 7. Now, as you can tell, we're starting off with this controversy about the Earth's atmosphere and the vacuum of space. Let's go see if he understands the second law of thermodynamics. So let's cue up the music and get going.
Now, the vacuum of space can't exist because it's connected to the non-vacuum of the atmosphere in Earth and all the other supposed planets that exist. So a vacuum must be a closed system, but they claim space is a vacuum and space is an open system. So it's philosophically impossible for space to be a vacuum.
Well, hi folks. Take a moment and meet the planet Earth, our beautiful spherical home. I'd like you to notice that we have brown continents, we have blue oceans, and we have white clouds. Those clouds are in our atmosphere. Here is a spherical planet with an atmosphere next to the black of space. Now I can almost hear the flat earth zealots saying, well, I've never seen that view of Earth myself, and there's no way that I could see it. Well, in that case, kindly meet Jupiter. Jupiter is a spherical, rotating planet next to the vacuum of space, and as you can tell, it clearly has clouds and an atmosphere which swirl around and move. Now, anyone that owns or can borrow or use a telescope can clearly see Jupiter. Galileo saw Jupiter. You can also see Saturn, Venus, Mars. These are all planets with atmospheres next to the vacuum of space. Now, many people in the flat earth say that this cannot happen because it would be a violation of the second law of thermodynamics. Well, considering the fact that it is happening and you can easily see it, obviously their understanding of the second law of thermodynamics is wrong. Let's take a moment and figure out why. Okay, so let's do one of the more complicated things that we're going to do on these videos. This is the second law of thermodynamics. Let's go ahead and say we have a container like so that has a valve in it. And then there's another stem to that container that goes to another container. Now, this container contains gas. This container over here is a vacuum. Now, what would happen if we open that valve? Well, obviously, gas would go this way, and it would equalize out in pressure on both sides. So if the pressure on this side was 100 and the pressure on that side was 0, we would end up with equal pressure on both sides, assuming the volume of these containers is the same. Now, at this time, it's important to talk about the different types of thermodynamic systems. Now, a closed system, which is what we just described, has two areas that are a container and some gas. And what happens is the pressure of this gas on the left, say, has a certain pressure to it. That pressure will push gas into the vacuum. It's a common misconception. Vacuums don't pull things. Things have to be pushed into them because they have higher energy and higher order, and they want to go to more disorder and disperse. Okay? But that takes energy on the part of the gas. Now, what happens if we have a slightly different situation where we've got our two containers, and this time, instead of a valve, we have a pump right here. Now, if we leave the pump off, what will happen is the gas on this side of the container will leak through the pump because, you know, it's basically a fan, and allow gas to come and fill the other side, which has, you know, a vacuum in it initially. Now, the difference between this and a closed system, this is what's called an open system. Now, an open system means that we can do work somewhere else, like at a power plant, where we reduce entropy or order by burning coal to generate electricity and heat, and we can send that electricity to a pump, and that pump can then be switched on, and it can reverse this flow, resulting in our gas on this side being pumped back over to the original side. But it takes an outside source of entropy to do that. Now, for example, if you look at the Earth's atmosphere, the Earth's atmosphere is not a closed system. It is an open system because energy or work is being put into the system. So we have the sun here. We've got the sun out here, and it's undergoing nuclear fusion and just throwing entropy out everywhere in the form of energy. Okay? A small part of that entropy is making it to Earth. Now, all this entropy out here is diffusing off into the universe. So, if you look at the total amount of entropy, this is all increasing in entropy. So, we can put a little bit of energy into the Earth and decrease entropy. So, even though we have a slightly decreased amount of S here, we have a massively increased amount of entropy out here being dispersed out. So, now here's the point that most flat Earth people seem to fail to understand about the second law of thermodynamics. If we have a package of air or atmosphere that is at sea level, that air will have a certain temperature, a certain volume, and a certain pressure. As that air comes up, say it goes up to 20,000 feet, what happens to this? The temperature goes down, the volume goes up, and the pressure goes down. All of that is a positive increase in entropy. Now, this packet of air right here has a certain amount of energy in it. That energy is in the form of its temperature and its pressure. And it also has a certain amount of entropy. It's packed into a small volume, and it wants to expand, it wants to reduce, and it wants to go down. All of these serve to increase entropy. Now, as this continues to go up, it's going to reach a point that it is very cold. The temperature is as low as it's going to get. The volume is massively expanded, and there's nothing to drive more of a expansion, and the pressure is almost non-existent. Now, you recall from the Red Bull jump, the pressure went from sea level when they left to like 9 Pascal when they were up at 120,000 feet. That's why Felix had to wear essentially a spacesuit or a high altitude suit. Let's look at one other aspect of the atmosphere. If the atmosphere was indeed a closed system. Now, no energy in, no energy out, just a volume of gas at a set temperature. The pressure here would be the same as the pressure here. And that is because in this entire container, there would be no reason to have a pressure gradient. Now, if we make it an open system, we can have more gas come in from the ground in the form of, say, volcanic eruptions. We can have matter come in from space in the form of, say, meteors. And we can have energy in the form of sunlight. Now, if this was closed, but we did allow sunlight to come in, what would happen would be we would get some warming. So, if this area here was warmed by the sun, it would heat up. That would heat the gas around it. That would cause the gas to expand. And by having that gas expand against this closed container, what would happen to the pressure in here? It would go up. Likewise, at night, the atmosphere would cool down, the gas would contract, and the pressure would go down. So, we don't see this on Earth. Earth is not a closed system. It is an open system. So the long and the short of it is that air that is going up requires energy to push it up. And there's going to be a certain point, it just literally runs out of energy. It can't really expand anymore. It can't cool anymore. And the pressure is almost non-existent. So there it stops. Now, if there's a vacuum above it, this is a near vacuum here too. So the difference between here and here is not really enough to drive that air. The air has no more energy to expand into that volume. So as a result, it stops. Now, what brings it back to Earth? Air has mass, and gravity pulls mass back towards the Earth. So, even though this is a relatively small part of the whole picture, the main reason that the atmosphere does not escape from Earth is that it only has enough energy to go so far. And then it just doesn't have any energy to go any further. And then what happens is the gravity starts pulling it back down. Now, the other thing that you can see in the atmosphere is what we call a pressure gradient. At sea level, we have air that's at sea level. And then for every 1,000 feet that we go up, we drop 1 inch of mercury. So we start at 29.92. At 10,000 feet, we're going to be at about 20. And at 20,000 feet, we're going to be at about 10 inches of mercury, from 29.92, almost 30. So, why does this occur? Well, again, gravity is pulling the mass of air downward. We can demonstrate this in a tube in the laboratory by filling the tube with butane. You can actually measure a difference in pressure at the bottom of that tube compared to the top of the tube. And it's an open tube. There's a really good video from BlueMarbleScience that I recommend you have a look at. So, this pressure gradient that we see right here is another reason that we don't have air blowing off into space. By the time you get up to the top of the atmosphere, which is about 62 miles, there's really no more air to leak out. 99.9 of the atmosphere is below that point. Most of it is below 20,000 feet.
The way that they fool us into thinking that this actually is plausible is threefold. First way they do it is in zero-G planes, which are Boeing 737s that do parabolic maneuvers that have a free fall illusion, a free fall effect rather, that happens for about a minute, where you can be floating in these planes.
Actually, no, Eric. Parabolic flight is a pretty violent maneuver. It goes from 34,000 feet down to 20,000 feet. There's only about 20 seconds of zero-G or microgravity possible on these things. Quite frankly, if you want to go more than that, you actually have to be in orbit to get more than maybe 30 seconds of zero-G.
And that's how they get this outer space look, like you're floating in outer space. The second way is through wires, harnesses, and green screen for the longer shots. In the ISS, for instance, they do that. And the third way, for like the outside shots they do, are in pools. They're actually underwater. And this is confirmed by the fact that there's bubbles rising in the pool in a lot of their shots. And people on YouTube have dissected a lot of the ISS and other supposed space footage and all the space bubbles that are coming out of their helmets. Some people are even wearing scuba gear. They found that as well. So that they fake these zero-G illusions by being in water, by being in zero-G planes, and by being in harnesses in front of a green screen.
Okay, now this is Canadian astronaut Chris Hadfield up on the ISS. Now what he's doing here, and please note the time. Let's see if we can get the time so that it shows a little better. There, you see the time? Now, what he's doing is he's taking a washcloth and he's wetting it down, and he's going to wring it out in zero gravity. You see the microphone floating there. You see the water droplets. You can't do that with wires. All right? The way water is behaving there, you cannot do with wires. Now, I want you to pay attention to the time here. Recall that I said that only 30 seconds, generally 20 at most, is how long you can fly in a parabolic aircraft. Watch the time on this particular shot right here. Notice too the bubbles in the tube of water on that washcloth. You notice how they're not rising? That's because buoyancy requires gravity in order to make light objects rise over dense objects. And there it is. You cannot do that with wires. You can't do it with a green screen. And you can't do that in a parabolic flight for this length of time. So that's pretty much that. Now the full 18-minute video of this interview is available on the internet. Look at his watch too. You see how his watch is acting? That's not wires. That's zero-G. You can see the full 18-minute video on it's a link in the description for this video, but it's uncut, all 18 minutes long from start to finish, and all in 0G. Completely impossible on a parabolic flight. So hopefully that puts that to rest.
And that makes us think that it's possible that out there in space you could just be kind of floating around like they show us in the movies. But as far as we'll ever know, as far as you or I would ever know, we go as high as we can in a plane or a balloon or a rocket, and we come right back down. Even the rockets they send up, if you're honest about it, you'll notice that they don't go straight up. All their rockets start a parabolic curve, they start to arc over, and the ones they claim are successful are the ones that go out of view before they come all the way back down.
Okay, now here's a view from the ISS. Watch the rocket launch where that white arrow is. You see it? It's coming up. All right, it's just clearing there. Now it's coming by that gold line. You see it coming up, and you'll see the stage separate here shortly. See? That's the stage separation. I think you'll see the second stage re-enter the atmosphere here in a minute. Obviously, this is a time lapse. All right, let's go see. Yeah, you see the core re-entry? And it burns up in the atmosphere? I don't know. I think that's pretty remarkable. So there's a rocket going up from space.
And if anybody asks, why do they always curve over like that? They just say that they're going around the curvature of the baller.
Now here's a very common misconception by flat earthers, all right? Rockets do not go straight up from the ground. Rockets go up and then they roll over to a parabolic flight. Now the reason for that, the reason that they generally launch towards the east rather than in other directions, is that they want to obtain what's called orbital velocity, which is about 17,500 miles an hour in order to stay in low Earth orbit and fall all the way around the Earth without falling back to the Earth. To do that, they gain speed and then ease over and start going parallel to the ground. Now, the reason that they launch east rather than west is the Earth rotates from the west to the east. And in Florida, for example, it's rotating at almost 800 miles an hour. If they launch to the east, they have that extra 800 miles an hour trying to get to that 1700 or 17,500 miles an hour. If they launch to the west, they will have to actually add that extra speed before they can achieve orbit. Now, if they launch to the north and the south, it's again, they're not taking advantage of the rotation of the Earth, but they're not fighting it either. So that's why rockets generally launch off to the east and why they go up and then go over. They aren't splashing down beyond your horizon. And by the way, how far is your horizon on the flat Earth? Couldn't you see them no matter where they dropped? I guess they go behind the curve of the Earth. Well, guys, I think that's about enough for today. We're going to have another episode on Eric's misconceptions about space in a couple of days. I believe he's going to be covering his misunderstanding of Newton's laws of motion and how rockets work in a vacuum. So, this is Bob the Science Guy signing out from Northern Michigan. Hope you like and subscribe to my channel, and we'll see you here in a couple days.
This rabbit hole's too deep for me.